Hello dear classmates, welcome back to the diagnosis chapter. In this video, we are going to introduce a special topic about scan chain diagnosis. We will introduce the full model followed by some important scan chain diagnosis techniques. Before you watch this video, you need to have knowledge about DFT, which is in Video 11. You also need knowledge about force simulation and the combinational ATPG, sequential ATPG, and also logic diagnosis. So if you have not yet watched video 11, please watch video 11 before watching this video. We know that scan chain is a very popular DFT designed for testability technique. According to some report, about 5 to 10% of the silicon area are occupied by scan chains. So the failure rate of the scan chain cannot be ignored. For example, there are some papers talking about 30% of the failed chips are caused by scan chain failures. So testing and diagnosis of the scan chain is a very important job. Typically, before testing a CUT, we will apply a so-called scan chain integrity test or flush test. As the name suggested, in this flush test, we simply shift in a 0-1 alternating test pattern such as 0011, 0011 to the scan chain, and we don't perform any capture. We directly shift the pattern out. Ideally, we should expect the same scan output as is shown in this figure. In this short scan chain, which has 6 scan cells, starting from the scan input pin, we shift in 6 bits 001100, and we don't perform any capture. Ideally, if there is no mistake, we would expect the same 001100 at the scan output. This flush test is important because we have all transitions occurred in this scan flush test, including 11, 10, 01, and 00. So, in summary, scan chain flush test is needed before testing a CUT to make sure the scan chain itself is good. Now let's see the effect of a faulty scan chain. Typically, a scan chain is indexed from scan output to scan input in increasing order. The number in the squares are the index of scan cells. Suppose that we have a stuck at 1-4 at the input of scan cell 2. Please note that this 4 is located at the scan input, not the data input of scan cell 2. Those scan cells whose index is smaller than 2 are called downstream to scan cell 2. And the other 3 scan cells whose index are larger than 2 are called upstream to scan cell 2. Now, suppose we shift in 001100. Let's perform this flush test. When these 6 bits are shifted into the faulty scan chain, the first 2 bits would be flipped to 1. So the downstream flip-flops will be affected by the fault. And then when we shift out the scan chain, the other two zeros will be flipped to ones because all the downstream zeros will be affected by the fault. So we can see that at the end we would observe all 1 at the scan output. This slide shows 8 popular scan chain fault models. Suppose we apply a 0011 alternating flush test. The good expected output should be like this. If we have a stuck at 1 fault in the scan chain, then the output would be all 1s. Those mismatched bits are highlighted and underscored in red. Similarly, if we have a stuck at 04 in the scan chain, the scan output would be all zeros. Suppose we have a slow to rise fault which is 1 cycle later than expected, then we would have this kind of scan output where the rising transition is 1 cycle later than expected. Similarly, if we have a slow to fall fault, the falling transition will be 1 cycle later. The setup time for ST is a combination of both slow to rise and slow to fall fault. Again, we have fast to rise fault FTR, which means that the rising transition is earlier than expected by 1 cycle. And the fast to fall fault is the opposite. The falling transition is 1 cycle earlier. And the hold time fault can be 1 cycle earlier in either rising or falling. This could be caused by hold time violation in the scan chain. Please note that in this table, we assume there is 1 single permanent fault in the scan chain, which means that the fault always happens consistently. Now it's time for you to have a quiz. Suppose we apply a flush test to a faulty scan chain. The expected output is supposed to be like this, but the observed output is like this, where the mismatched bits are highlighted in red. Please identify what kind of fault is this. I will give you a hint. This is an intermittent fault. That means a fault may not always happen. Okay, have you got it? Since the rising is 1 cycle earlier and the falling is 1 cycle earlier, so this is a hold time fault. However, some of the transitions are correct, so this is an intermittent hold time fault. Have you got it correctly? Now let's introduce the first method to diagnose scan chain faults using sequential ATPG. This method was proposed by Kundu in 1993. The idea of sequential ATPG is simple. Since we cannot use scan chain to control the flip-flop, we will use primary input and the sequential ATPG to control the flip-flop. In step 1, we control the flip-flop to our desired value by sequential ATPG, and then in step 2, we shift out the scan chain and check if the value is the same as our expectation. For example, given this sequential circuit, there are 2 flip-flops, flip-flop B and the flip-flop C. Suppose we want to detect if there is any stuck at 1 fault. downstream to flip-flop B, then we would need to control flip-flop B to 0. So, in the first cycle, we set the primary input A to 0. Since this is a controlling value, so after one system clock, the value of B will become 0. And then, at this time, we shift out the scan chain by 2 cycles. The expected values should be x0. If we successfully observe flip-flop B to be 0, then there is no stuck at 4 downstream to flip-flop B. Otherwise, if we observe a 1 in flip-flop B, then there is at least one stuck at 1-4 downstream to flip-flop B. So the idea is very simple. We can repeat this process to every scan cell in the chain to locate the 4. Now let's use sequential ATPG to do the similar thing. Here we show an example, but now we want to diagnose the stuck at 0-4. So we want to control flip-flop B to 1. But can we do that? In the first time frame, we apply A input to 0. After one system clock, flip-flop B will become 0. But at this time, flip-flop C is still unknown. So even after the second system clock, flip-flop B is still 0. That means we cannot control flip-flop B to 1. In summary, we failed to generate sequential patterns to control flip-flop B to 1. So we are unable to diagnose stuck at 0-4 downstream to flip-flop B. This shows the limitation of this method because sequential ATPG is somewhat ineffective. Now it's time for you to work on a quiz. John has a very smart idea. He says that since we know there is no stuck at 1-4 in the scan chain, we can first shift in 2 zeros in the scan chain. So now flip-flop B and C are initially 0. Given the initial state 0-0, can we use sequential ATPG to diagnose if there is stuck at 0-4 downstream to flip-flop B? That means we want to control flip-flop B to 1. Is this doable? Now please pause the video and think about this question. Okay, have you got it? In the first time frame, B and C are both 0. So this is 0 and J is 1. After one system clock, the content in the flip-flop C would be 1. So at this time, the output of the OR gate is 1. At this time, we can apply primary input to 1. So in the third time frame, B flip-flop will become 1. And then we can shift out the contents of the scan chain. If we observe a 1 correctly at flip-flop B, then we show that there is no stuck at 0 downstream to flip-flop B. So this is a smart modification proposed by John. Have you got it correctly? Since the sequential ATPG may not be useful for large circuit, now let's move on to the simulation-based diagnosis. We will introduce the technique of X simulation proposed by Intel in 2001. In this technique, Guo proposed to use X simulation to identify the upper bound and the lower bound of the fault. We assume that the faulty scan chain and the fault model is already known by the flush test. So we can perform a circuit simulation where the faulty scan chain values are all changed to unknowns x. In this way, we can obtain simulation values. For example, in the following figure, suppose this is a faulty scan chain. There are indexes from 10 all the way to 0, from scan input to scan output. Now, after the X simulation, we obtain simulated values in blue colors. Some of them are deterministic 0 or 1. Some of them are unknown, because during the simulation, we force every scan cell of the faulty scan chain to unknown. And then we test the CUT on the tester. We can observe the actual values from the tester. The green color shows the actual values that we observe from the tester. By comparing the simulation value and the observed value, we can identify the lower bound and the upper bound of the fault. The lower bound is defined as the maximum index where the observed value is equal to the simulation value, but they are not equal to the stock values. For example, for index number 0, they are the same. For index number 1, they are the same. For index number 2, it is ignored because the simulation value here is unknown, so we cannot make any judgment. For scan cell number 3, their values are the same. They are both 0, which means that up to here, the fault has not yet occurred. So we can say that the lower bound of this fault is number 3. For index number 4, although their values are the same, but actually this is the same as the stochastic value, so we cannot make any conclusion. For index number 5, there is unknown, so there is no conclusion. For index number 6, now we start to see mismatch between the simulation value and the observed value. This is the upper bound of the fault because the fault must have occurred downstream to scan cell number 6. So now we identify that 6 is the upper bound and the 3 is the lower bound of the fault. The actual scan chain fault must be between 3 and 6 in this scan chain. Now it's time for you to work on this quiz. Suppose that we already know that there is a stuck at 0 fault somewhere in this faulty scan chain. Given this simulation output and the tester observed output, please identify the upper bound and the lower bound of this scan chain fault. Now please pause the video and work on this quiz. Okay, have you done yet? Starting from index number 0, they are the same here, and index number 1, they are the same. We ignore number 2 because this is unknown. For scan cell number 3, they are identical, but this value is the same as the stochastic value. so we don't count this. For index number 4, they are the same. That means the 4 is upstream to scan cell number 4. So number 4 is the lower bound. Now let's move on to 5. This is a known, so we ignore it. And number 6, they are the same. Number 7 is the known. For index number 8, now we start to see mismatches between simulation value and observed values. So we know that that 4 must be somewhere downstream to number 8. So the upper bound is number 8. The actual defect must be somewhere between 4 and 8. Have you got it correctly? Now let's introduce the last diagnostic technique, Single-Excitation Pattern, proposed by Lee in 2005. The idea of single-excitation pattern is very simple. Assume that we already know the faulty scan chain and we already know the full model by flush test. We can load a single excitation pattern to the faulty scan chain. A single excitation pattern has only one sensitive bit that can flip by the fault. For example, suppose that we know that there is one stuck at 04 in this faulty scan chain. Therefore, we can shift in a single excitation pattern 1, 0, 0, 0, 0, and etc. into this scan chain. The bit 1 is called the sensitive bit because only this bit can be flipped by the fault. The other bits is guaranteed to be correct. So now, after we shift in this single excitation pattern, we can generate a test pattern to detect the single stuck at 4 at scan cell index number 10. If we are successful, then we can diagnose this scan cell. And then we can move on to the next single excitation pattern, which has only one single one at index number 9. We can continue to do this all the way move to the index number 0. So for this faulty scan chain, which has 11 cells, we have 11 different single excitation patterns. By doing this ATPG, we can diagnose the location of the scan chain fault. So this single excitation pattern technique actually turns the diagnosis problem into a simple single stuck at 4 ATPG problem. This is the contribution of this idea. Now let's see some examples. Suppose that we shift in a single excitation pattern which has only one 1 at this particular scan cell. We can easily generate a pattern to detect this fault. So this cell number 7 is diagnosable. Next, we move on to the next single excitation pattern. Now we have one single 1 sensitive bit at scan cell number 6. Since there is no logic coming in or out of the scan cell, this scan cell is undiagnosable. Next, we move on the sensitive bit to scan cell number 5. When we apply primary input equal to 1, we can sensitize this Fold effect and observe it at the output. So cell 5 is again diagnosable. In summary, in this faulty scan chain, some of the scan cells are diagnosable. We can successfully generate test patterns. For the other cells, we cannot generate ATPG patterns. In total, we have 11 cells in this scan chain, and we are able to generate patterns for 5 scan cells. So the average diagnosis resolution is defined as the total number of cells over the number of diagnosable cells, which is 2.2. In summary, scan chain occupies about 5 to 10% of the silicon area. So scan chain faults can occur in the scan chain, not the logic. And the testing and diagnosis of scan chain faults is important for yield improvement. To test for scan chain faults, we would need scan chain integrity test or flash test. We simply shift in 0011 0011 sequence, and there is no capture. We introduce 2 types of diagnosis technique in this video. First one is sequential ATPG, which is not practical for large circuits. The second type is X simulation. We can determine lower bound and upper bound using logic simulation. We can use ATPG to generate single excitation pattern so that we can diagnose some of the scan cells. Now, before we end this chapter, we want you to think about some questions. Question number 1. Since the scan chain faults do not affect our logic operation, why do we bother to test them? This is a good question for you to think about. Question number 2. If scan cell has a stuck at fault, can we detect them by regular logic testing? For example, if this cell is stuck at 0, can we just generate a logic ATPG pattern to detect it? Why do we need a special purpose single excitation pattern? Please think about these 2 questions. Thank you.